Alright, we should now be live again. Hello everyone, and welcome to today's video, where I'll be going over the Physarum simulation that I developed with the help from some friends. So this was quite a journey to get here. Originally I started with just a particle-based Physarum simulation, but that wasn't quite good enough. So I tried to replicate what people would do in programs like Godot in this case. So the way that this works is that we have both a grid, as we can see here, that's at 256 by 256 pixels. We can see that right over here, 256. And then the particles, which are the agents, as they're usually called. So the simple way that this works is that the particles leave behind a trail, and then the particles look at the trail that is on the grid, and then try to go towards the bright parts, given a certain little bit of logic. And I can show that logic really easily. So right here, it takes a look, well, over here we can see, the particle looks ahead according to the velocity, a little bit to the right by 15 degrees and a little bit to the left. Don't worry about that math. It's very technical, but that's just an optimization. And then it decides over here whether to go left or right depending on this little logic gate, and then by how much to move, or rotate in this case. And then it rotates the velocity based on that, as we can see right here. And then this last little bit is to make it so that the simulation will be infinite, so that the particles that go off here will teleport to the other side, or portal, and then it will continue over to there, which is very, very cool. Let's see, anything else? For the grid, it's extremely simple. It just looks at the particles, gets the distance, the proximity to the points, remaps it, adds it into this trail value that gets blurred a little bit and multiplied by a little bit less so that it fades over time. So nothing too complex there. But yeah, that's how it works. So I think now is where I'll start getting into the technical parts, the part I showed off over here. So it needs to find out where the trail is on the grid, as we can see here. It has to sample it 3 times, but that's very expensive. So how do I make it so that it knows which cell to look at without using the sample nearest node, because that's very expensive? Well, I found out that the grid here, this is very technical, so I'll go over it pretty quickly to not bore all of you. But this grid, the index starts at 1 and then goes to 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it goes in a kind of scanline pattern, so it keeps going up and up and up. Then I found out, wait a second, if I just take the grid, the particles' position, I can figure out what index they would be. So that's how I got the index in there, using this math, which is a little technical, but you can see it right here. And I apologize if it's too technical. But you could just use a sample, let's see, let's bring this out here and use a sample nearest node. Let's see, just sample nearest. And then it would do the same thing, but it's much more expensive. You would just have to hook that up into there and then feed that into there. So I wouldn't really recommend it, but that's the secret sauce behind this one. It just makes it a lot faster, so that it can run in real time. I would like to extend this to apply to the grid part right here, but the geometry proximity scales linearly with the amount of points, so it's not too much of an issue, but it could be sped up, especially once I get my hands on the for each loop. Alright, this is fairly advanced, well, extremely advanced from what I'm talking about, but that's just to get the data from the grid back to the particles right here. But the actual logic is quite simple. It's just if the value is greater on the right, turn right. If it's greater on the left, turn left. But if the middle is greater than either of those, then move in a random direction, and then it passes it along. And then it affects the vector rotation, and so on. So nothing too bad there. I apologize if this is a little confusing. This part took a lot of figuring out to get right, but I showed you the nodes, which should be good. But I do have to offset the input position by the velocity by a little bit, so that's looking ahead. I also add 0.5 because the grid right here is in the middle. It's not offset into here. So I hope that is understandable. It's just the grid needs to be synced up. This grid has to be synced up. The positioning is very important because this vertice has to be half a pixel in on both sides from where it would be, so that's why that's there. But that just has to be synced with what the particles are looking at, and then it just works. But yeah, there we go. So now it's time to play around with the simulation after that very, very technical talk. Let's go into the particle sim, and let's go and play around with the settings. I also have it so that over here, I should just showcase this real quick. I just take the trail value and then move the mesh up by a little bit, and then in the shader, I color it and do all the other fancy stuff, as we can see here. That's just for the grid in the background, don't worry about that. That could just be a texture, but I like doing everything procedurally. But yeah, so there we go with that. Let's start editing the values. So I'll go into the particle. Let's go into here. And let's mess with the rotation degrees. So this will cause it to be a much more, I don't know, it'll have much more control over the shape it creates. While previously it was a lot more random. So we can see this one is optimizing, as you would expect a Physarum simulation to do. If I bring it up by even more, let me just reset the cache real quick. As we can see, we get, oh, that one's actually very, very cool. Interesting. We get that happening, which is nice. But if we change it to even lower. Ah, okay. So we still get that kind of almost veiny pattern, I guess. Like it's trying to assemble. Oh, wait, the cache didn't reset. There we go. Sometimes you need to give it a little bit of convincing in Blender 3.6 to make it reset the cache. Let's set that back to 15, and we can see how it resolves so much better. Can it be applied to a 3D surface? Technically, yes, but it would still act as if it was a 2D simulation. Like, gravity, like, you can paste this onto a 3D model if you, like, render it out as a texture or something, but I wouldn't recommend it. Because it's just, not that great. Let's turn up the looking angle, so this looks, I would recommend looking at the documentation for proper Physarum simulations. They will explain it much more than I do, much better than I do. But this basically says, hey, look to the left and look to the right, but a little bit ahead of themselves based on this value, which this is basically the scale value. So if we do that, we can see that the simulation is just generally a bit larger. Oh, that looks really cool. Ooh, I'll have to remember those settings. But if we turn it down to be much smaller, the same thing will be happening, but just on a much smaller scale. I think with this grid resolution, we can't really see that all too well. So let me, yeah, there we go. Maybe 0.3. Let's try 0.3. Even though that start looks very, very cool. But yeah, there you go. And another thing about this is that it is seamless because of what, with the wrap node that you saw, that loops the positions. So if we take a look at this, let me go into the other view. It portals to the sides, so it will fill out into a grid, which is very cool. That's something that's a lot easier to do with just texture-based approaches. With, you know, tools specifically built for that, you can just check it so that it loops around. But this is pretty cool, too. I'm trying to mimic what people do with GPU simulations in Blender. Like, I'm very surprised that this works in Blender. I thought it would be way too laggy. And to be fair, it would be almost too laggy if it weren't for the optimizations that I put in place. Mainly that ID grid lookup thing. Because the sample index node is so expensive because it has to search through all the points on this grid several times for all the points and all of that. But with the method I had, it just, or no, the points, yeah, that points have to reference that. But with the method I did, it's all parallelized, basically, where each one just takes its position, automatically knows where it is according to the grid, and all of that just works. In the famous words of Todd Howard, it just works. I would like to get 16 times the detail, but unfortunately, I'm limited by the technology of my time. We do not have GPU compatible simulations yet, but that would be really, really cool. Will this be a paid product or just experimenting? This one would probably... I'm not sure if I'm going to release it just yet, because there's still optimizations that can be made, and those optimizations are hard to explain, as we can see in this live stream. Like again, the particle grid ID lookup right here. This math took a while to figure out, but it's basically looking at the position. It also wraps to make the thing seamless if you want. And then you basically put in the resolution of your grid here, and then it figures out what ID in kind of the TV scan line, the do-do-do, 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 it would be in, matching the mesh grid. I hope that's somewhat explainable. I did compact all these nodes so that I would have a cleaner viewing experience, but that also does make it a lot harder to copy. So I'm showing the nodes in high definition right now, just so that you can see everything clearly. And then the sample index nodes, pretty straightforward. And then again, the actual brain of the Physarum, pretty simple. And then the start points, pretty simple. The velocity and all that, the wrap, pretty simple. So beyond the one technical problem, which is the ID thing, to make it faster, this would be very simple to make. It's just that one little technical quirk that made it difficult. There's the easy way to do it, but that's the slow way to do it. And then when I get the for each loop node, I can make it even faster. I hope. It's currently being developed. I saw in the Blender dev chats that they're currently working on the for each loop, so once I get my hands on that, this could get even faster, which will be very cool. So yeah, let's do just a little bit more experimenting. This will be a rather short live stream, because we're only at 12 minutes. Ooh, this one's very cool. I remember this one. Oh, that's so... like, it makes, like, the donuts, which is a little gross. Like, I made this purple so that it would be less gross, but there are much worse options, color options that I could make. Still deciding on which kind I will post. Oh, that is so cool. And if I turn this up to, say, 60, what happens then? Oh, it's kind of doubling up. Very cool. Now let's set this to 90. Okay, okay. Oh, wait. It's turning into orbs. Very interesting. I want to try to see, like, how far I can take this system. Because it could be... like, it's simulating it's mimicking biological functions. In this case, the slime mold. And I want to try putting in, like, food values and see how that affects the sim and various other things. But it'll be cool if I can figure it out. So, yeah. But then again, I might need the for each loop just for speed and such. And I also like the textures. I was able to figure that out quite well. Let me turn this to be 5 degrees once again. Reset the cache. Just have to shake the object around so that's forced to update. Now let's go with a very... I keep going low and high turn radius, but let's just go and up that by quite a bit. Okay, that's turning almost into reaction diffusion. Interesting. Makes sense, though. Actually, that almost looks like bacteria clumping up and such. So here we can see that happening, and then it just turns into the plague, essentially, which is cool. Very, very cool. Let's try that. Interesting. Okay. Another type of plague. So let's just try... I want to see what the relation will be like. Like if I bump that up over time. Let's set the turn radius to 10 degrees. Oh. It's just doing a death spiral. So let's go and fix that. Let's set this to 170, which probably will not work all too well, but I still want to try it. Negative? It's trying, but nothing too shocking there. Let's set it back to what we know works. I should probably save it in that state as well. But yes. What was the settings that I had before? Was it 5 degrees? I made it look even cooler. There's one value that I had that made it look like rivers when they start bending and then they bend too much and then they re-find the shortest path. I'm not sure if I can find that again, but that would be very cool. Or was it 5 on this side? Let's just try 5 and 5. So we're getting that very veiny look again, which makes me feel a tad uncomfortable. So something like that. Close. Very, very close. 15 degrees. Oh, not bad. Why don't I set it to negative? Oh. Okay. Turns into waves. And then if I do that again, it reforms. So, dissipates and reforms. There we go. Special thanks to Chris for helping me out with the math behind this. I had it fairly close, but I missed a crucial part of the logic, which was using the center. I completely missed the center sensor, which basically makes all of these patterns possible. So I just had the most basic version of it, but I was missing that very, very crucial piece. Alright. But yeah. Is that the correct? That seems to be rather correct. But yeah, once again, it tiles, which is actually fairly gross. I do kind of like that version of it. But it just looks so much... Like, the resolution is only 256 by 256, which is so painfully low. But with the displacement, it helps override all of that, so to speak. Okay, let's set this to 100. In one of the versions, well, in this version, I had, and I can go and bring this over to here, a method that would go and limit the bounds to a circle. This is probably not the best version of it, but I'm just going to connect it so that we can see what happens when it hits a wall, and then tries doubling back. We can see that it's trying to communicate with that side, but it's fine. So that's what happens then. Let's go and do that. Oh, that's so cool. And then it reorganizes. That is so incredibly cool. 25. Let's go and shake it up again, so that has to redo. Like, I think that's my favorite, just because you see all the actors and then it slowly reforms. Oh, okay, maybe not my favorite, because it does look a tad disgusting. Let me set this to be 20 degrees. Let's try to make these both the same, 25 and 25. Okay, wait, let me reset the cache once again. So it looks good at the beginning, but the one downside is it's too good at optimizing itself to the point where it's, you know, it just turns into that, which isn't as impressive. I want to really showcase its ability to make the patterns. Like, something like that is a bit more impressive looking because, yeah. Set this to 30. Again, I keep flipping between these modes, but it's cool. I want to see all the settings and see how they interact. Well, that one's pretty cool. Let me set this to be like 2. Let's see what happens then. So, do-do-do. 5. Mm-hmm. All right. So I should probably make a better bounds algorithm, which actually, you know, that's probably fine. Yeah, no, it's probably fine. But the bounds were made for the circle so that I can actually have it look like a petri dish. It does make it a bit messier with the node layout, but it's good for what I am testing for now. Let's go and do that. I believe this value being at 25 was one of the best. So that I will save it in the good version, in the best looking version. Let's see. Was it 5 degrees? Yep, I think it's 5 degrees. Like, it just looks so much more... Like, you can see it assemble into an organism. What FPS and bitrate do you stream at, by the way? I stream at 30 frames per second. And bitrate, I honestly do not know. Okay. Let me... Again, 45. No, smaller turn radius is better. So wait, I had that at 5, right? Let's Control Z. Oh no, I had it at 8. I'd say that's a good middle ground. You can see it form very, very quickly. Let's try 20. Really try to hone in the settings there. No, that's actually looking a little bit worse. Reset the cache once again. Okay, that's the one that I want to go for. Good. Let's save that. And then, let's see, let's go into the shader. I can show you the alternate shaders for this. So one is just purple, you know, very basic. But then one is a little more realistic looking. But then I realized, oh wait, that looks fairly disgusting, even though it is accurate. So I'm still wondering if I want to post that version or the much more palatable purple version. Which actually, let me implement the hue shift in here. And then I also had some dots in there to kind of simulate the cell look. That's not bad though, making it really pop. Just a little bit of hue shift, and it looks so much better. And then I could make the hue shift even more apparent. Maybe not. And that looks just way too much like blood. Like those are just veins at that point. It's like, ooh, blood, I want to avoid that, but let's see how realistic I can get it to look. Just really quick. Kind of like that, and then it gets darker. Yeah. Okay, let's rewind that into, again, a more palatable hue. Purple. So it looks science-y, not quite, disgusting, grotesque, and all that, even though it still kind of looks like that. Alright, so we have that, and that. I think I will fiddle with the settings a little bit more. I think I'll probably end the stream at 30 minutes, just so that I don't go over. I already explained it as well as I could, which probably wasn't all too satisfactory. This isn't a tutorial per se, it's an overview. Because this required some very technical stuff to make it fast enough to work in the viewport. Some very, very technical stuff. That one's not bad. Okay. Okay, yep. You can see it form. So maybe 6 degrees? Just a little bit more. It's optimizing, but it's not optimizing too bad. I also want to see in this shader editor, again, the index scan line thing, like, just having the index of the grid be projected in, like, having the index of the grid match up with the index that's being fed into the particles thing here, that's what makes it fast. So this grid just virtually matches up one-to-one with the grid. That's what makes it fast, or else this would probably not be real time. Again, trying to treat this more like a GPU simulation rather than a CPU one. But getting the data to feed back using that method, I think I would need the for each loop to do, which unfortunately we don't have access to that technology just yet. So here, once again, here's basically the inverted view, which is pretty cool. Even though I could alter it a little bit, so that looks a little bit more like an X-ray. I'm so happy with how it just looks like an actual living organism. Like, throw a little bit of lens dispersion on that, and then it'll look like a microscopic thingy. And then maybe a little bit of like color shift. Like, let me just do a little more to this, so that's just gets bright, and then it shifts a little bit to the other thing. Let's set that to black. Or no, I want that to be white because that's handled separately. So here we have that, and then we just shift it ever so slightly into one of the things. And then maybe add in some, I don't know, like a blurry image in the background is kind of like the out of focus real world and all that. Would be pretty cool. I'll experiment with that. But I do fear that, I fear that the resolution being limited to 256 by 256, just for an example, if we do that, that's how many pixels I'm working with. Not nearly enough for something too complex. But yeah, let's go back to 1080. So the current stream is at 1080p. So the simulation, this whole simulation takes up a quarter of that. And the timings, oh wait, I forgot to show the actual timings of the sim. So for the grid portion of it, let me just reset it. That takes, again, let me reset it. This is the most expensive part, where it is around 8 milliseconds, again, because of this node. It has to go over every single particle, and then look at the distance to every single point on here. Not exactly the best, not the fastest. But with the particles, these simulate. Right now I have 50,000 particles, 25,000 particles. It could handle 50,000. But 25 is enough for now, but this runs at around 3 milliseconds. If you were to use GPU simulations to make Physarum, like one example that Chris made, had 16 million particles and a texture of 1440p. So significantly higher resolution and way more complex, well, way more complex on a visual side. The math was still fairly similar. But with that, you can just get so much higher fidelity. And it might allow, with that much processing power, it might allow for 3D simulations of Physarum and various other things. Like, that's how they make real-time smoke simulations in Unreal and Embergen and so on. So if we somehow get the GPU to work, like even if the for each loop node was GPU accelerated in some way, like we would have so much power, and we can possibly make real-time smoke simulations. But again, that's a big ask, because geometry nodes is still very, it's very much based on the CPU. So for it to transfer over to having some GPU functionality, the devs did talk about it, but it would be a tall ask. Well, right now we're still trying to get the basic features in at the moment. Like the active camera node, we still don't even have that, unfortunately. Even though it was proposed, and I believe a node was made, but it just wasn't developed on. Alright, so there's that. So that's the Physarum simulation. I think we'll wrap this up here at 30 minutes. Final questions. How did you show the time of each node? That is a simple drop-down right here. You can switch wired colors, context path, annotations, timings, and named attributes. So it's right in there. What about blue or green? We can try blue or green really quick. I'll just chop out the hue shift so that we can try... So here's blue. Let's try a different blue. Alright. I am looking forward to the AGX color space in 4.0 because Filmic apparently is really bad with colors. Like, the blues don't really show up as well, the purples don't show up as well. AGX is a bit less saturated at the basic settings, but if you turn up the contrast, you can get it back. But it's much more realistic, especially with bloom. So, I would recommend looking into that. So here we have green, which is very cool. Like, which one... I'm still torn between green and purple. Like, purple, I think, looks the best overall. But green gives, you know, the kind of cool science-y goo glow. Still unsure. I'll do some more testing. Let's test it right now. So we have green there, and a little bit of a hue shift. So I could make it more like that. Actually, that's looking a lot more plant-like. Which I think is probably better, to lean into the plant aspect rather than the fungus aspect, because that just looks really, really bad. So maybe a little bit more, just picking the plant-like colors to really showcase what part is where. I guess that also kind of tries to simulate the subsurface scattering in a way. But yes, there we go. And then maybe let's try this out a little bit more. Okay. Like that. Let's try switching this to hue, saturation, and value. Oh, that could look cool. Doing it the other way, not so much. Unfortunately. So maybe a little more into there, just really lean into those. Yeah, I think that's... Yeah, that's very plant-like. I think I'll go with that for the post. A lot less obtrusive than the yellow version. Alright, that should be everything. Thank you all for watching. This was a very cool project to work on. I think it's almost done, but I need to get... The only part that's left is to optimize this using the for each loop node, which will be in 4.1, we hope. But until then, this is the final version. So again, thank you all for watching. This was a very fun project to work on. Now we'll see you in the next live stream. Have a good one. Dismiss.